Okay, this part, let's see, what we're working on is just buffering. Now, the way I do it is not how a lot of people do it, and that's okay. I mean, I just use a simple transistor. A lot of people use an Opamp to do it, or they'll use a JFET. There's different ways to do it. I've just found this circuit to work very well for me, and so I'll just kind of show it to you. Here's kind of a close-up of it. The power supply's on there. Let me bring it up this way. Okay, this is and I'll explain this. It's a pretty simple circuit, but this is what they call an emitter follower. Now, actually, most emitter followers, they'll kind of have a form like this. Let me kind of draw it out a little differently, because the way I do it is, a lot of times, it's not quite the same. This would be like a typical emitter follower. It's going to have this configuration here. We'll just do it like something like this. Be biased like this. See there. So this kind of biases it. You know, obviously this is 9 volts. This is 0. So this kind of puts it in the middle there. And you know, the signal coming in here, it's going to see 3 different things actually. And I'm just going to just do this for a minute. Okay. Let me zoom in on this and we'll talk about this a little more. So signal comes in, and for AC signals, the input impedance, you have to trace all the paths to ground or to the positive, because they're both from an AC standpoint considered like a ground. So if you trace this way, your signal's seeing 220K. If you trace this way, your signal's seeing 220K. So it's like it's seeing 2 parallel resistors, and then these input impedance would be 110K. But it's actually seeing a third way. There's a third path that's going from the base down through here to this ground. And the impedance it sees across there, it's real easy to calculate. It's going to be this resistance times the HFE. So let's say, it's 10,000 times, let's just give an HFE of like 200. Okay, so that's 2 megs. So 110K paralleled with 2 megs, well, that's just 110K basically, because this is so large comparatively, then you can just kind of ignore it. So anyhow, so how do you choose these values? You can, you know, a lot of times people will choose it so that this, this right here times HFE, if you make that much larger than this, you can just ignore it. And that's kind of a common thing engineers do. They'll make this arbitrarily large, or they'll get like a really high gain transistor, and then you just can ignore that and you just look at this stuff. I mean, that's fine. This is a really common configuration. What you're going to see here, though, is if you look at the input impedance, you get an input impedance of 110K versus something like a meg. So, you know, this is one reason I don't always use that. I do sometimes, but so how you're supposed to, and why do you want this to be way larger than this? Well, it's because you don't want this bias affected. This is part of the reason. See, you're using these 2 resistors to set this value right in the middle. So if you put something that competes with this one, it kind of drags that down. So, you know, this is a really common configuration, And I'd say this is kind of a rule of thumb, if you will, that if you want to find like how big of a resistor you should use here compared to there, well, usually if you take this number and you multiply by 10 for an HFE of 100, and then you double it, you're right at 200K. And so that's kind of a rule, actually, I don't infrequently use, as you sort of multiply this by 10 and double, and it's kind of a rule of thumb for the ratio of here to here. That works pretty well usually. So this is fine. Now let's move over to this one. Then again, this is less common, but I use it. Yeah, I use it because it just makes a bigger input impedance, but it's not as reliable in terms of exactly what you get, but it's usually always better, or many times better. And let's just explain that. Okay, we mentioned here. Let's look at this circuit here. So I'm just going to get rid of this. Okay, let's do that again. All right, so we said this should be about 4.5 volts, and it is. There's 4.5 right in the middle. Let's put a little delay on this signal, just so we can see it a little bit better. So we can see the bias better. Okay, so here's the signal. We delayed it a little bit, and that you can see where this is. This is just the signal. Now when you look at this bias here we go. It's right around 4.5 volts. It's slightly lower because it's got this third leg that's kind of dragging us down a little bit, but barely, right? So basically this is so much larger than that. This is at 4.5K. Now what about this? This is the actual signal we're using. Well, it's not 4.5 because it copies the signal from the base down to the emitter, same phase and everything, but it subtracts off like 0.7 or so, because this is sort of like the diode drop, silicon diode drop. So we're going to see that. There it is, the copied signal. It's about 0.7 less, and so that brings it down to like 3.6 or something like that. And then of course you've got this DC decoupling capacitor, and this will bring it down to 0 volts. So let's compare the input and output. Input is there, output's there. You can see they're basically the same. There's tiny loss, you can barely see it, but it's of no consequence. And why a buffer in the first place? I mean, I guess we haven't talked about that. But the point of a buffer is the signal sees a high impedance or high enough impedance. It copies it. It puts out same signal, but this same signal has a lower impedance. See, every time you go from one stage to another, you're supposed to multiply by 10 in terms of the impedance. So, like if, well, anyways, that's what the buffers are used for. And I mean, I can show you that in the circuit here. I kind of assume that people already know that if they're watching this, but let's look at the preamp real quick. Let's see here. Yeah, we'll go with, I guess we'll go with this right here. Okay, here's the compressor. You've got signal coming through here, and the output impedance is like 100K, I would say. Yeah, because we've got this is going to ground basically, so it's 100K, or if anything else is parallel in the circuit with it, it drops out a little bit more. So you can kind of plan on 100K as being safe. So you need to go into a meg. So this output impedance is 100K. Input impedance here is going to be like 1 meg or more. So that is a step going up from, by a power of 10. Now, why is that? I mean, this is, I guess, we're getting, well, tell you what, I'm just going to talk through that real quick. But why you're going up a power of 10 is basically the voltage divider is being formed. I'll bring up this computer program I wrote. Okay, yeah, here it is. Source impedance, there's a voltage divider and a load. It's sort of like the input impedance and the output impedance are forming a voltage divider, and so there's going to be a drop in voltage. And if you make that ratio like 1 to 10, you don't really lose that much, you know. So in fact, here we can make that 1, make that 10, and you've got 0.9 of the signal coming through. This is a calculator I made, by the way. This is kind of aside, but every time I need to do something, I always look it up, and I got sick of looking up the same thing all the time at different websites, so I put them all on one of this little calculator here that you can bring up, you know. So if anybody wants that, leave in the comment sections, I'll get it to you. So anyways, let's get back to this. So let's just walk through this so that you can see, because you know this isn't really a common way to do things, but I found it to be useful. Again, I'm trying to share things that you don't see in many other places. Now, why am I doing this? Well, this actually is it's not as precise. Like you can see here, the bias is set pretty closely, and I mean, if you get an HFE that's, I don't know, 100 versus 300, it doesn't make that much of a difference, really. Now here, if you basically, the input impedance and the bias are going to be based on the HFE, and so it's a little bit less precise. And let's look what this is with 3 megs. And again, this is a simulated transistor. So we've got, where's the bias there? Whoop. Excuse me, I gotta take this out and copy this one in. That one has the time delay on it. Okay. Yeah. Alright, so here's our input signal. I've got 2.5 volts here, by the way. That's a pretty big signal. Yeah. Anyways, we'll talk about that too. That's another consideration. Let's see here. This is the bias at the base. It's right now, because of the HFE is set at 4.91. The output comes out to 4.2. The problem with this, if you say it's a problem, is going to be that the way you figure out where this bias is you have 3 megs here, and you're going to take this 10,000 multiplied by the HFE, and if the HFE was like 300, that's 3 megs, and that should put this exactly in the middle. The fact that it's above 4.5 just a little bit suggests that the HFE in this simulated transistor is probably like around 330 or something like that. Now, if you, it's kind of hard to simulate, I think, but let's put like a different transistor in. Let's pick this one. I bet that bias will drop a little bit. Yeah, it went down to 4 volts there. So this is below 300. Now, can't really simulate it, but let's just say you put a transistor in, and it has a, I don't know, let's say the HFE is 150 or something like that. I'll bring up my little calculator. Let's see here. So we're going to have 10,000 times 150. That's going to be like a 1.5 meg resistor. So we're going to put 1.5 here. We're going to put 3 here. And let's see. And let's see here. So this is sort of the biasing we're using this at. So we're saying that that voltage is going to be 9 volts. So that basically, this is a voltage divider calculator. You can look this up anywhere. That basically puts this at 3 volts. And then you subtract off 3 volts minus 0.7. Oh, excuse me, 3 minus 0.7, 2.3. So if you have a very bad transistor, it's going to drop down to 2.3 here instead of like 4.5. So, you know, that could be an issue if you're going to clip, if you get a really bad transistor. And the other thing that happens is, let's look at this. Let's look at this here. If you have 3 meg resistor, 1.5. What I'm doing here is I'm saying, well, this is 3 megs along input impedance this way, and for a low value transistor you get 1.5 megs across this leg. Calculate parallel resistance. Okay, it's calculating it to be 1. So that's 1 meg input resistance. Now if this is higher, it's 1.5. So it's kind of like if you have a very bad transistor, poor HFE, then this ends up dropping and you lose headroom. You also lose, you go from 1.5 meg input impedance down to 1. And so it's totally dependent on the HFE. The problem is, or the lack, like I say, it's not really a problem. It's never been a problem for me because I've never gotten a transistor that low. Now I'm sure more experienced older people have, who have built more things, but even if you get one that's really low, it's going to work. You're just going to clip, you know, at like 2 point some volts. That's not a problem for the circuit I built. Just going to open this up. Let's see here. You know, all these things. In fact, the way I did this is you get signal loss all along here until it's reamplified, and you get a lot of signals that are sort of you know, knocked down a little bit through this filtering. Certainly here you're basically never going to exceed the headroom, except for maybe in this circuit, maybe initially, like you could have really hot pickups and have these transient clipping, and that could, I guess that could be an issue. But practically speaking, like I've checked hundreds of transistors and I almost never get anything lower than 300. And there's also an easy way to check here too, is when you have this hooked up, if you want to say, well, boy, did I get a bad transistor, maybe you've already soldered it in, you're not even sure. All you do is just take you don't even need an oscilloscope, you just take like a multimeter and you hook it up to ground and you put the positive here, and whatever voltage you read, that's the bias, you know, where you could look right here. I hate to make things too complicated, because this functions so much better than this almost all the time, and I've never had a problem with it. And actually the transistors I've used have been fairly uniform. So I don't know. I know it's, you know, so that's why I use this here, because it just performs. I've never had a problem with it. But you know, you do need to think about, in tight situations where you need really good tight control, you want to make sure you design things correctly. And if you can't tolerate, if your circuit can't tolerate those sorts of ambiguities in terms of the impedance that it's seeing, or the actual biases have to be real precise for some reason, then that could be a consideration. But I hate to throw the baby out with the bathwater and never use this. I use it when I think it's fine to use. And so again, I'm talking about a circuit that I don't see used that often, that I use, and I'm sort of explaining why. But I do understand, using other things. Just since there's not that much talk about this, I'm gonna kind of do something else. I never planned on this, but I tell you what, if you're interested, you could stop watching now if you want and just say, well, gosh, I know everything I need to know about this, but there's some neat things you can do here. And okay, there are two things that you can do to make this different, make it perform differently or more precisely. And I'm going to show you the first way, which is neat. It's kind of an older thing. You don't see it too often, but it's called bootstrapping. And here's how it works. We know that this is a signal right here, right? And it's a copy of the signal, but it's just 0.7 lower. So you can take that signal and you can feed that back to the base and fool it into thinking that it's, higher impedance than it really is. And let me just explain it as I go. So you take the signal here, right off your emitter follower, and you feed it back to the base. Okay? Now we're going to disconnect this from here, and we're going to put a resistor here, like 10K or something like that. And then instead of hooking up this here to this node here, we're going to skip that whole node. Sorry, it's maybe not the best. We're going to go straight to the base. Now, it's a couple extra parts. They're passive, but it's kind of neat. What happens here is this is actually, technically, it's not negative feedback. It's positive feedback, but it's positive feedback that's less than 1. So your signal comes in here, comes out just a little less than 1, comes back and feeds itself in to the base again. But this thing here, the signal's coming in, and now it has to split this way, which is high impedance, right? That's like we already said, that's the impedance across here is going to be 3 megs or something like that. It's the HFE times this. But then the other way it goes is this way. And normally you'd say, oh, that's just 10K in parallel with, that's 10K plus the 110K parallel we talked about earlier. However, because we fed this back to here, it sees a higher impedance there, because the way you figure the impedance across here is sort of the current going across there. And the voltage divided by the current is the impedance, and that alters the current here basically. So let's just kind of look at that. I think this is neat. I have built this before. It's awfully neat. But we're gonna just look at that, and just a second, got a dog issue. Okay, so this is I just redid this. This is our original circuit, really common when we talked about initially, like how most people make their buffers, these emitter follower types, real common design. So let's look at the input impedance that this source sees, and we're going to do that the same way. I'm going to change this. See, that's a different amplitude, but okay. I'm going to run this. This needs change to AC analysis. Make 32 hertz, 16K. Okay, close out of this. All right, so let's look at this. Here is voltage, current. So we're going to divide those two. Okay. And get rid of this phase. Set this to linear. Okay, so here is our input impedance. It looks like a big curve, but really it's not. If you look at the scale over here, it's 1.595K versus 1.58. So this is, you know, if you zoom out, this is really trivial. So this basically is an input impedance of 105.8K, 106K. We said it was going to be 110 or a little less than that, and it's just a little less than 110, just as we predicted. Now here, we're feeding that signal back to here. Let's see what we get with that. Now that is the voltage. Here's the current. Divide the two. Get rid of this. Wow, look at that. Here's the first circuit right over here, and this blue circuit is right here. We've got an input impedance of 817K, almost a meg, by just adding these two parts. You didn't need to use a JFET or an Opamp, and really it's just one transistor. So this is an old style way, a little older design. I've built this, recorded it, and even looked at the noise on it and so forth. But not professionally. I mean, I just kind of used a spectrum analyzer on it and recorded it and looked at the baseline floor noise and that sort of thing. And it was noisier than quieter ones, but I mean, it was totally usable. I mean, with my own ears, going through studio speakers, I really couldn't tell that much. In fact, I couldn't tell at all. But I could see the noise floor was, you know, I mean, it was all, to me, like the noise was all low because I couldn't really hear it. But, you know, it could make a difference, I mean, potentially, if you're amplifying small signals or something like that. So, you know, that is kind of a neat trick. You can get it up higher than that by altering these values a little bit. I just picked 10 microfarad and 10K, which is sort of on the order of it. Now, let's just check the biases and see if they've changed. I mean, they shouldn't have, but we're going to go ahead and run this. Okay. See what happens. Okay, so remember, we said the bias here was 4.5 or about. And let's see what we've got here. About the same thing. I mean, it's just slightly lower, probably because of this. Let's see if the output is 3.8. Let's see. So see, our biases haven't really changed. So you get the picture. It's a neat way of modifying a basic emitter follower to make it high impedance, and usually you'll see, I mean, just whenever I've seen this, it's usually written like this, and that's kind of I've seen it that way, just like that. Now, there's another way you can get a decent emitter follower configuration or early buffer, and then this uses 2 extra parts. The other way to do it is just making a Darlington configuration. That's kind of old school too compared to what people do now, but honestly it's worked fine for me too. I just don't use them because I generally get by with just using the one I typically use. But if you want to, all you do for a Darlington, again, this is 2 more parts. Basically, this is your base, problem with the buffer is you generally want a buffer to be high impedance, and this really isn't that high of impedance. So this, it is low output impedance, though, but not really super high. It's like, not as high as you'd like it. So another way to do that is you do what's called a Darlington configuration, and I'll just draw that out. And that's a really neat circuit. I think it's really cool. But okay, so it's 2 more parts. 2 more parts than the regular. It's an extra transistor, so it's actually. There we go. So what you do is, let me just talk through this. The Darlington is basically, you get a low impedance output going into a high impedance input at this base with another low impedance output. So technically the HFE is supposed to be like the HFE of this times that. It's like kind of like a super transistor or something. So this is usually a configuration. You've got the emitter of one going to the base of the next one. Then you've got this like that. And usually this whole conglomeration is called a Darlington configuration, where it's usually just, like it's usually drawn out kind of like this. Sorry about that. Oh. Okay, so it usually looks like this. This whole thing is kind of called the Darlington. These two together with the emitter going to the base. And the problem with it this way is, like, the HFE of these transistors is a little bit dependent upon the current going through them. Let me just show you that, actually. Again, my trusty calculator. You can see, depending on the collector current, the HFE depends on that. You see this on different sheets and so forth. So, running this into here, there's not much current going through there. So you kind of like, you can hook this up and tie the emitters together. And that kind of fools it gets more current going through here, and it sort of raises the HFE a little bit. They work better that way, although I've admitted this before and it does work fine. Sometimes they'll sell this as a conglomerate. It looks like one transistor, but really that's what's inside. And sometimes it'll have that resistor in there too. So we basically looked at this circuit. We've added 2 parts to it. We've added this transistor and this one into that Darlington configuration. Let's see what the input impedance is there. So let's give this a try. Actually, since we're on this, we'll look at the bias first. Bias, there you go, 4.5 volts, 4.476. Right here, output. Now that's something else to think about. There's more of a drop here, actually, going from, you technically do lose a little headroom, although I think it can be exaggerated in these simulations sometimes. I think it's less than what you think it would be. I think classically they say, well, if you got a 0.7 volt drop here, another 0.7 volt drop there. So you can take that into consideration, that you lose more headroom basically using one of these. But I don't know. It's not usually an issue, but it could be if your signal's pushing it and you don't have that much voltage to work with. Let's go ahead and try this. I'm going to try checking the. Let's see here. So I'm setting up this Bodie plot. We're going to see what the input impedance of hold on. Before I do that, I forgot to change one thing. Since this has such a huge input impedance because it's just this massive transistor, you can just go up on this to like 2.2 megs. That's kind of the point. I failed to mention that. I'm kind of talking as I go. So this would be like a Darlington type buffer. So we're gonna delete that, get rid of the phases, make this linear. Now I'm expecting, yeah, we got 1.1 basically. There's this drop off here, but you can see this, it's all above 1 meg. Well, I'll just throw this on here for comparison. This is going to be the kind of the lower impedance version. Okay, so this here that I just plotted was this ordinary emitter follower with the input impedance of around 105. This is all the way up here over 1 meg. So again, add two parts, either this way or this way, and you end up getting this enormous increase in input impedance. And by the way, the output impedance is lower on this also. Not so here, but so those are kind of like some other neat ways to make buffers with simple parts. I'm not going over the Opamp because that's what everyone uses. Or not everyone, but I mean, that seems to be the modern way to do things, although I find this just as elegant and easier to use often. Something else I think we should talk about is just sort of like the current that these things can put out. And what's the output impedance of these things? Well, let's just focus on the simple one. So we talked about the input impedance and the kind of the biasing of those different circuits, and I think you should consider the output impedance. Now, an ideal buffer has a signal come in, there's a big input impedance, there's very low output impedance, and it's in phase with it. You know, that was basically an ideal buffer. It just copies a signal. It's like a big block with, you know, high impedance on one side and low impedance on the other. So this has very low impedance. I'm going to change this to just 3904. Okay, so, but they're sort of like, you know, these transistors, they can, there's differences between them sinking and sourcing. And like they can source a lot, but they can't sink as much, and that refers to like how much current they can draw through in one direction versus the other, like when the signal is going up or down. And so people have gotten around this by doing things like complementary pairs and things like that. You know, just since we're talking about it real quick, I think I should just mention that there's a configuration called a complementary pair where you use a 3904 and then a 3906 in like kind of like a push-pull configuration, or a complementary pair would be actually more precise. And you can look this up too. It's really similar. And then there's also something called a Ziclay Pair. I don't even know how you pronounce it, but see if I can sort of. There's different configurations. I guess they're kind of similar or the same thing, but I mean, I've never built one, but I'm sure they function better really than even the Darlington configuration. But anyways, so what's the output impedance here? You're supposed to take the preceding stage, like let's say that this, well, let's just draw it out there. Let's say that, you know, you're going from this stage into this stage, and this has, I don't know, 10K, well, the input and output impedance of this is going to be 10K of this stage. But then you go into this bigger one, it's like 1 meg. And so what you do is you take the impedance looking backwards, you divide by the HFE. So like in this case, it's going to end up being like 10,000 divided by say 300, for example. So that's like 33 ohms, very low. So that's awfully low. Now it's not low enough to drive like headphones or something, because headphones may be like 8 ohms, right? So, but I mean, for a lot of circuits, it's considered low impedance. So, and looking back, I mean, I'm using 10K here because this has zero or source impedance. This 3 meg thing also is so large compared to this that you just use that. But the point is, you look backwards and you say, well, what's the impedance? Then you divide by the HFE to come out. And then you divide by the HFE and get that. But we're going to talk for a minute a little bit more about just the output impedance of this and really how much current it can supply. Because those are kind of two different questions, I'm told. Okay, so just looking at this circuit, let's run this and take a look. Okay, and there's the input, there's the output. Yeah, we're on the wrong thing. Let's see here. Sorry about this. Okay, we're gonna turn this to transient. Okay, let's looky here. We've got input and output. We'll look at the base. Okay, so this is kind of what the signals look like. Why am I showing you this? Well, okay, we're saying this is like 30 ohm output impedance, and we're going into this huge, compared to 30 ohm, it's huge. So we're running into 100K. Well, you know, this is a little overkill here. This is, you should be able to go into like a lot less than that. But the problem with these, if it is a problem, I mean, so at least you have to know about this. See, this is a 2.5 volt signal, right? 5 volts actually. It's 2.5 peak to peak. Now you can see this is cutting off, right? And why is that? It's because it can't supply enough current to this load. The load's too low for that, for a signal that big. If you increase this load a little bit, let's say, that looks better. So like if you have two, even though the output impedance is considered very low for small signals, when you get big signals there, the transistor has trouble supplying the load correctly, going back and forth with these really big swings. So as a rule, it's another rule of thumb I use is like, if you have a 10K resistor here, I never put a less than 10K load on it unless the signals are really small. And I usually at least double it, or you should go as high as you can. But that, in a way, it sort of defeats the purpose of using, you know, you say it's a super low output impedance, yet you can't even run it into 10K without it, you know, sort of clipping. Well, it's just because it's a really big signal. I mean, if you're running like, I don't know, maybe say a volt or something, say 1 volt, I mean, then you're fine. I mean, it looks great. You can probably even lower it lower than that. I don't know. It's just okay. Let's see what happens there. You know, it's starting to overall just kind of become lower, but so this, you know, this is something to think about, like how much current can this supply. Let's just do a quick experiment there. We'll say this is a 22K load, and we're going to make this voltage variable. Then I'm going to, you know, so we're going to run this up to, we'll just run up to like 4 volts in increments of 0.1. So this should take the parameter V and vary it from 0 volts to 4 in increments of 0.1. I think that's the right statement for it. Let's give it a try and see how long it takes. Maybe that's wrong. Yeah, I think it's, I think I wrote this wrong. I think it's supposed to be dot step param V. Let's see if that works. Okay, there it goes. It's going up, it's going pretty fast. We'll just wait on it. Okay, here it is, going from 0 to 4 volts. Let's look at the output. Okay, so it only makes it to like, say that's 3 volts. So it starts clipping at 3 volts. So, you know, you're looking at a, let me see where the, so yeah, it's clipping right here at 1.3 volts. So anyways, it looks like you can get up to like using sort of a 9 volt battery. You can produce signals of like up to 6 volts peak to peak, which isn't bad, with sort of without a whole lot of signal loss. So that gives you an idea of this concept of, you know, not having a big enough load. So there's 3 volts. Yeah, that's pretty good. So that gives you an idea of the output impedance and the fact that you have to still have a load on it. That, and you know, depending on how much voltage you're trying to push through here, the transistor can only put out so much current. So you got to make sure you have a big enough load. So I think that's probably enough on buffering. I mean, we really talked about a lot of stuff, but the key is I will mention one more thing. Is sometimes these emitter followers, you know, you put them in circuit somewhere and they can, I mean, actually any circuit you build with amplification in it and power supplies and so forth can have oscillations that develop or noise and things like that. And one way to sort of stop that or block it sometimes is putting in like a little base blocking resistor, like right there, like 1K, or right here, or even on the output. It's good actually, at least as far as preventing oscillations from further stages, to add a little bit of linear resistance. I usually put up 1K there. Now you don't always need to, and so you can kind of build circuits and test them and see if they're needed. I always just throw them in because you never know what you're going to necessarily be hooking up to, and it's one less thing. I mean, you build something complicated, you don't want to have problems while you're trying to get it to work. So I almost always just put a series resistor here before and after. If you're building like a standalone, let's see there. If you're building like a standalone buffer, you usually put what they call a pull down resistor on, and that would be like you've got something like this, a little series resistor afterwards. Then you'll put, if you're expecting to go into, you know, like 10K or something, you just put 100K on there, and that just kind of keeps it at ground. Like if you're hooking things up to it and disconnecting from it, it's keeping this at ground. And so that's kind of a good thing that's usually done. I'll give you another trick real quick. You can change this if you want. You can change this to a pot, like so. Just make this like, I'm just representing this like a pot. You can put this on the wiper, and then you can use this whole thing as a volume control. That's another quick and dirty way to throw in a different control, like if you want a volume on your buffer. Now if you move this up and down, as you move this up and down, you're actually moving the bias up and down also, and that'll sort of equilibrate across here. But if you move it up and down really fast back and forth, like on a slider or something, on like a mixing board or something, you'll get kind of like some transient DC offset, which kind of can sound like a big like oomp or whoomp or something. So it's not for like really fast moving controls. You'd want to use this volume, but that's, you know, it's not usually a problem most of the time. So I think we'll just call it a day on these buffers. That's plenty talking about. But if you have any comments or suggestions or even critiques, because, you know, hey, if I've said something wrong or I'm not interpreting something right, you know, you let me know. But well, thanks for watching.